think this is the right slide. Yep, that's the right slide. Okay, so today we are going to talk about chapter 5 and 6. It is an extension of what we mentioned before. So back in week 2 and week 3, right, we mentioned about like histogram or the distribution. Right? Histogram, you see different value and the frequency and the relative frequency, right? You see that chart. Last week, we learned the mean, median, mode. We learned the variance, standard deviation, right? That's the center and the spread of a distribution of any data set. And we've seen the symmetric bell-shaped curve. We've seen the positively skewed distribution and the negatively skewed distribution. So all those knowledge is the foundation of today's lecture. Because today we are going to talk about calculations in probability distribution. We will talk about how to best describe a distribution, like how to best describe your data set using the central location, using the spread, and more importantly, how to locate one number in this entire distribution. So simple example, I just told you, well, the average homework 2 score is like somewhere in the high 80s, let's say 88. And if you got a 92, you'll be like, am I just like the middle, right? The majority, the middle 50, 60%, or am I actually already like top 5% of the class? Well, it really depends. It depends on the distribution. So today, through the calculation, we will be able to figure out exactly like where your number is, given the rest of the class. You just need to know the mean, the standard deviation, and your own score. We have a formula to learn, and we have a table to look up. And with that, we can get it very precisely for every number in the data set. Where is it? Is it at the 20th percentile or 28th percentile, or is it the 53rd percentile or the 99th percentile? We can get to that level of precision. And also just had a high level overall understanding of, again, what probability distribution is. How do you calculate the mean, the standard deviation of that? So that's the plan for today. We start with chapter 5 because it's simpler, and then move on to chapter 6. Chapter 6 gives us the generalizable operation of how to calculate everything. But in chapter 5, we start with the basic concepts. We have talked about variable, right? What is a variable? Variable is something that we're interested in, we want to measure, we collect the data about. And in week 2, we talk about, okay, like which department you come from could be a variable. I could also collect the data on a variable of your gender, right? Or a variable of your age, or a variable of your address, or a variable of your hair color. And so any information, any fact we collect could be a variable, maybe numeric, maybe non-numeric. But when we talk about a random variable, we are talking about a numeric description of the outcome of an experiment. So now everything needs to be in the number format. It can be text, right? Like your address, now it's not a random variable. Gender, if you write male, female, that's not a random variable. However, you can create a code book and you say female coded 1, male to coded 0, and then your data set will have like 1, 1, 0, 1, 0, 0, 0, 1, right? So that's okay because that is numeric. So you need to do a little bit of transformation sometimes for those categorical variables. But as long as you have numeric description, you are good for a random variable. And for random variables, sometimes people categorize them to be discrete random variable versus continuous random variable. A discrete random variable may assume either a finite number of values or an infinite sequence of values. While a continuous random variable may assume any numeric value. So the key difference is a discrete random variable have values that you can't take or values that don't make sense at all. But for continuous random variable, there's no limits, no constraint on what value you can take. I can give you examples. So if I want to count how many students came to class today, I log in Zoom and then students start to log in. Okay, I see 1, 2, 3, 4, 5, blah, blah. And then now I have 11 students. There may be more logging in later, but I'm counting the whole numbers when I record the variable of students, right? Students coming to class today. I have to record a whole number. A number like 8.5 doesn't make sense, right? I cannot have any decimal place. I cannot have 9.75. Those numbers don't make sense. So if my random variable is number of students coming to class, then the constraints, it has to be a whole number. Like between 8 and 9, there's no value I can take. Like there's a gap. If there's a gap anywhere along the interval, you got a discrete random variable because again, the gap means discrete, right? If you got a gap anywhere, your variable is discrete. But if you ask me, how many miles did you drive yesterday? Well, I can just do some simple vague estimation. I tell you, I drove 10 miles yesterday. Or when I check the meter, that's really precise. It may show like, oh, actually it's 10.2 miles or 10.234 miles, right? So it can go as many decimal places as I want, as long as the meter is precise. There's no value I can't take, right? Like between 10 and 11, there is no gap. I can take any value. Like I drew just a little bit back and forth, count 0.002 miles. That's all okay. So like distance, that's a continuous random variable because there is no value that I can't take. There's no gap along the interval. So that's the difference. Wanted to see if you understand the concept. Can anyone give other examples on discrete random variable? Ongoing stats for sports. For example, like what exact metric? You need to be more precise. Hitting averages. What it could be. So is there any value you can't take? Oh, okay. Yeah, well, yeah. If no, speed is not, because right, I'm talking about discrete variable. So there is no gap when you measure speed. Right? It could be any value. Think about it. Or you tell me, is there any value you can't take? If you have a super precise measure goes through 4, 5, 6 decimal place. So speed is actually continuous random variable, but yes, number of CPP alarm, yes, that is a discrete random variable because we're counting people, right? We're counting 50,000 people or 4,538 people. Yes, it has to be whole number, right? There is limits. There's a gap between the whole number. Yes. So number of alarm, shoe size. Yeah, we have to go like 5, 5.5, 6, 6.5. So there is a 0.5 gap between, right, each size we can find on the shelf. So any number between 5 and 5.5 does not exist. We do not have a 5.2575, right? Like it's either 5 or 5.5. So yes, that's a very good example. What other discrete random variables we got? Other examples? Yes, very nice, Kent. Number of cars manufactured, right? You got to have a whole car. You can't have 0.7 car, right? 1 car, 2 cars, 3, right? How many cars? Eyesight. Yeah, that's a good one. You got like 1.8 or 1.3, 2.0. Oh yeah, okay. Yeah, 2020 vision. Yeah. Yes. Yeah, that is discrete because you just got those limited numbers you can take. Yeah. Very nice. Those are all good examples, right? And we can also measure how many households there are in this community, or how many faculty we got at CBA, how many people are there in your family. So usually, if it gets to how many, right? Usually, if you have to count something, it is a discrete random variable. And a lot of times, if you have like the standardized scale that's created by human, right? Like shoe size, right? Like eyesight, those human created scale, a lot of those are also discrete. So we got those type of variables. And now who can give examples on continuous random variable, right? Like distance or speed that there's no limit to what number it takes. Any examples? Height, yes. Yeah, Melissa and Hector both got it. Yes, yeah, height, right? If we have a very precise measure, we can see, oh, are you 5'5" or 5 feet 5.25 inch, right? Or are you 172.53 centimeters, right? So yes, height is, it can go as many decimal places as you want. There's no gap, right? People could be taller, shorter, any value. Yes, temperature, very good. Now is it 68 or 68.2 or 68.25? I mean, as long as you get a precise tool, you can measure the value to as many decimal places as you want. Yes, temperature is. And similarly, yeah, you're faster than me, Ken. I was just about to say volume. Yes, volume of, milk product, volume of anything, right? In milliliter or liter or gallon or ounce. It doesn't matter the unit, but you can take any value. There's no gap. Right? Maybe this bottle is fuller than the other bottle, right? The other bottle is 0.002 ounce short than your bottle. I mean, that happens, right? We check how do they fill in the bottles in the standard way, or is it short? So yes, volume. So like speed, volume, distance, temperature, height, time, right? So those measures are continuous. And the easiest question you ask yourself is there any value I can't take? If the answer is yes, there is a value or there are certain values you can't take, you got a discrete variable. If the answer is no, you can take any value, then you got a continuous variable. So that's how we want to differentiate and categorize the variables. One last tricky question. If I have a variable to measure the price of the textbook, is it discrete or is it continuous? Price of your textbook. Discrete. Brenda got it. Everyone else? All agree? So then who can explain why it is discrete? Hector got it. So who can explain why?
It's because it prices to the nearest penny. You don't have fractions of pennies.
Yes, exactly. You got 100% of it. Because when we measure price, it only goes to the second decimal place, right? Only to the cents. You can't get a fraction of cents. So if it's labeled 67.99, right? $67.99. The next you have to go $68. There's nothing like a 67.9999. You can't have more decimal places. So there is a gap between 67.99 to 68. Like no value in between can be taken. So that's why it is a discrete random variable. Very nice. Yeah, I see you all got the concept. In another class I'm teaching, I think it's at my Thursday or Tuesday class, the people are struggling a little bit. Like half of them got right, but half of them didn't get it right. But I'm happy, like you here are all saying it's discrete. So that's the basic concept. Chapter 5 starts with the easier one, the discrete random variable, because we are simply counting number, right? I mean, or most of the examples are counting number, like 1, 2, 3, 4, 5 students. And when you have those very distinct values, it's very easy to identify the pattern and easy to do calculation. Chapter 6 deals with continuous variable and how we normalize everything, how we create a measure that applies to discrete and continuous random variable. That's for chapter 6. But we start with chapter 5. So here, typical example of discrete random variable, right? Again, measures how many. So we create the variable to be, right? Let our random variable to be the number of TVs sold at the store in one day. So just how many TVs are sold. So this X value may be 0, meaning we didn't sell any TV in a day. Maybe 1, meaning the store only sold 1 TV. Might equal 2, that's the store sold 2 TVs on that day. It could equal 3, right? The store sold 3 TVs, or if the store had a really good day, then it sold 4 TVs. And so those are just whole numbers. We can count the TVs sold, and then we can get to 0 probability distribution just based on that number. So this goes back to the concept of histogram. Remember at the beginning when we look at customer invoices in the auto repair shop, right? How much does it cost? And then we see, okay, in the 50 to 59 range, there were only 2 invoices. In the 60 to 69 range, there were 13 invoices. In the next category, there was like 13 or 16 invoices. So just by looking at the number and do a tabular summary, gets us to actually the distribution, or we call the relative frequency of the values. So that is the foundation of probability distribution. The probability distribution for a random variable describes how probabilities are distributed over the values of the random variable. So it means we first need to know what value our variable can take, right? Did we sell 1 TV or 2 TVs or 3 or 4? What's the best day? Well, best day we sold 4 TVs. What's the worst day? Well, worst day we sold 0, right? We wanted to see what value X can take. And then we see what's the probability of each of those happening. And do we have a high chance to have a good day, or is there a high chance to have a bad day? That's the whole concept of probability distribution. This is more of a review of week 2 or week 3, sorry. So here, we got like all the numbers recorded, right? TVs sold, and another column of frequency, right? How many days? So here we can read that out of the total of 200 days, 80 days, the store sold 0 TV. And 50 days, the store sold 1 TV. 40 days, store sold 2 TVs. For 10 days, it sold 3 TV, and for 20 days, it sold 4 TV. So that's the frequency. And remember, we mentioned to calculate relative frequency when we learn about histogram. And now in the context of probability distribution, that relative frequency now is called probability. And the notation for that is f of x. So f of x meaning the probability of x value. So now we calculate the probability, or again, we say the relative frequency by using the frequency of 80 divided by total frequency of 200. So we got 0.4 for x equals 0. But the frequency of x equals 1 is only 50. So 50 divided by 200, then we got this relative frequency of 0.25. And then we calculate for the rest. So now this one, now the table on the right-hand side is a probability distribution. So you got to have two components, what your x value is and what's the probability of that value. And you have to cover all the values in your data set. You can't miss anything. Because ultimately, your probability should add up to 1 or 100%. So that's a full probability distribution. Again, we've seen it in week 3, but now we're just reviewing it. And then there's a one-to-one mapping of the graphical representation. In the graphical representation, the horizontal axis is always the value of the random variable x, and the vertical axis is always probability. So that's the design of histogram. And then, right, it's just a mapping. When x equals 0, probability is 0.4. So you see 0 with probability 0.4. The next value would be x equals 1, and the probability is 0.25. So 1 with 0.25. So we map that for all the variables. And this is the probability distribution. You can show it in graphical representation, or you can just show it in tabular summary. They mean the same thing. So that's the very basic. Any questions so far? Question? No?
Show us the graph again real quick.
No, we're good? Yes, okay. Okay, good, no question. Okay, good. Yeah, you can type in the chat window, or you can just unmute yourself. I told you on day 1, I'm totally fine with you just unmute and speak. So that's the basics. Now let's look at another example here. So in this example, we create a new random variable. That in this example, the random variable x is the number of heads that appear on the toss of 2 coins. And we want to determine the distribution of x. So I got coin 1 and I got coin 2. I toss those 2 coins and I want to record how many heads do I get. Right? X is the number of heads. So again, it's a count number, right? So in this situation, when I have 2 coins, coin 1 and coin 2, I toss the coins and I want to count how many heads do I get. In this situation, what's the possible value that x can take? What are the possible values of x? And again, this is a count number. What's the smallest value we might get? Zero. Yes, very nice. Very nice. Yeah, Brenda, Hector, Jason, very nice. Yes, Melissa. Okay, perfect. You got it. Right. if I got tail, right? Coin 1 shows tail, coin 2 shows tail. Well, then I got 0 head. So yes, X can possibly equal to 0, and that reflects the outcome of tail. That's a frequency of 1. Then can I possibly have 1 head from tossing 2 coins? Is that possible? Yes. Yeah. Okay, good. Yeah. Sharina, Brenda, yes. Yeah. Right. If I have head, tail, or if I have tail, head. So in the 2 situations, I have a count number of 1 head. So X equals 1, but the frequency is actually 2. It's head, tail, or tail, head. What about X equals 2? Right, if I'm lucky, I got head, right? That's a situation when X equals 2. So frequency is 1. But that's all I can possibly get. If I only have 2 coins and I count how many heads I get, I can only possibly get 0 head or 1 head or 2 heads. I can't have 3 heads if I only have 2 coins, right? So X only has a limited value to take. And then let's figure out the probability. Because here we see there is a total of 4 different outcomes, or a total of frequency of 4. So 1 out of 4 translates to a probability of 0.25. And we write it as the probability of X equals 0, which is f of 0 equals 0.25. So make sure you understand the notation, because a lot of times people are not going to spell out everything. This means the probability of X equals 0 is 0.25. These are just write f of 0. And then similarly, when X equals 1 is 2 out of 4 frequency, which is a probability of 0.5. And then when X equals 2, we got frequency of 1 out of a total of 4. That's a probability of 0.25. So here in this distribution, right, we see 0, 1, and 2 with probability of 0.25, 0.5, and 0.25. So do we all understand this? Yes, Brenda's good. Hector good, Melissa good, Jason, Ken, very nice. Okay, thank you. Yeah, I like to see the feedbacks, so I can move on. So that's the most basic, right? Now you see what X is, what f of X is, and this full set of X and fx is the probability distribution. That's what we get to do manually. Sometimes we can use a formula to determine probability distribution. The easiest is a uniform probability distribution function. So in a uniform distribution, the probability function is 1 divided by the number of outcomes. So to make it simple, we don't even have 2 coins. I only have 1 coin. If I want X to show, again, number of heads by tossing 1 coin, there are only two outcomes. It's either I get a head, so x equals 1, or I get a tail, x equals 0. Right? So in that case, there are only two values x can take, and there's equal chance for the two values to happen. So the probability of each of those is 1 divided by 2, because only two possible values, x equals 1 or x equals 0. So that's how we calculate uniform probability. It's just 1 divided by number of outcomes. Similarly, if I throw a die and I let x be the number of, right, let x be the number I see by throwing a die, then we can have 1 or 2 or 3 or 4 or 5 or 6. So there are 6 possible outcomes. And again, each one will just be 1 out of 6, equal probability. And that applies to a lot of situations. If I see, okay, I got 18 students on my roster for today's class. If I randomly call a name, what's the probability that your name get called? Right? It's simply 1 over 18. So that's this uniform probability. Simple, straightforward calculation, but I do want you to remember, like, understand that this is uniform because each probability is the same. And then with all that calculation, now we can tie it back to the concept that we learned last week. Last week, we learned to measure central location and the variability. So the central location, most of the time we use the mean to measure. So here we can calculate the mean for any random variable. In this context, sometimes people call this expected value, but it is the mean. So again, you can use the words interchangeable. You can call it the expected value, but you can also just call it the mean. So it is actually the weighted average of the values the random variable may assume. And if it's a weighted mean, right, we need to know what's the weight. The weight is a probability. So what we got to do is, again, we need to have x value. We need to have the probability of x value, so f of x. And then remember in the weighted mean calculation last week, remember the template, right? I did column B times column C, right? So that x times f of x is what you get for each value of x, and then you take the sum of that. That's the exact calculation of weighted average. Right? Again, remember your weighted GPA, the weighted average of what you get for this class, right? So that's the same calculation. So that's the mean for a random variable. The variance is also very similar to what we saw last week. The variance is a weighted average of the squared deviation of a random variable from its mean. And again, the weights are the probability. So same concept. We learned the concept of standard deviation, right? The average of the squared deviation between your x value and the mean. So same as last week, we get to do the deviation. We get to do x minus mu, and we get to square that deviation. And then now, with the weights being probability, we just need to multiply that squared deviation with the probability. And then take the sum of that and get the variance. Then same as last week, we can calculate standard deviation as the positive square root of the variance. So that's how we calculate the major metric to measure the center and the variability of your data set for any random variable. And going back to this TV sales example, and we see, okay, again, 40% of the chance the store sold 0 TV, 25% of the time store sold 1 TV, 20% of the time sold 2 TVs, so on and so forth. So x times f of x at 0 times 0.4, the product is 0. Then 1 times 0.25, the product is 0.25. 2 times 0.2, it equals 0.4. Then 3 times 0.05, we got 0.15. And finally, 4 times 0.1, we got 0.4. So the expected value is 1.2, which again is the mean, right? So you can actually interpret it as on average, the store sells 1.2 TVs in a day. That's what we're calculating. Because each value shows up with different frequency, different probability. So using that probability as weight, the weighted mean, right, of TV sales is 1.2 TVs. That's what we're calculating. The mean sales. And then we can do the same for variance. So we got the x and we just calculated the mean. So x minus mu, right, 0 minus 1.2, we got negative 1.2. Then 1 minus 1.2, we got negative 0.2. Then 2 minus 1.2, we got 0.8. And we do that for all the x value. Then next step is to do the square. So negative 1.2 squared is 1.44. Negative 0.2 squared is 0.04. 0.8 squared is 0.64. So we square everything and then multiply by the probability. So we got that for all the x value and finally take the sum. And that is the variance of this random variable. And the square root of that, 1.2884, is the standard deviation of TV sales. So it's not hugely different from what we learned last week. It's almost a repetition, but we just understand that now incorporating the probability, we can still calculate the mean, the variance, and the standard deviation. And everything is weighted by the probability. So that's all we're doing. Any questions so far? Like calculating mean, variance, and standard deviation? No questions? Good. Everyone else? Yes, okay, okay. Okay, then if we move on to the next topic, we want to look at a special case of random variable. If we look at the sales, right, okay, you may sell 0 or 1 or 2 or 3. So there are many values x can take. Nor if we count how many students, right, also many values I can take. I may have 8 students, I may have 10 students, 11 students, 20 students, right? So when x can take on multiple or more than 2 values, we just keep using the formula we just learned. For a very special situation, if x can only take 2 values, then we have a binary variable. And we actually got to follow binomial probability distribution. So again, it's a special case. And usually or later in the textbook, you will continue to see something measured by proportion. Anything like a binary will later be measured by proportion. So if you read the book, you will know that for the binary outcome, we got to focus on the count number of the two outcomes. And as another translation between statistical language and plain English, we have to define the only two outcomes to be success and failure in statistical language. So it's very different from real world or plain English context. Success does not mean you accomplish anything, and the failure did not mean you failed anything or you didn't do anything. Success versus failure are the statistical term we use to describe two outcomes, the only two outcomes. So what are the variables that we get to use the binomial distribution? A simple example, in my class, I can ask, how many of those are senior students and non-senior students, right? Senior students can't wait, but non-senior students, if they don't register, they can still register later. But so senior students versus non-senior students, right? Everyone must belong to one of the two categories. And I can simply define senior students to be success and non-senior students to be failure. Or I can define senior students to be failure and the non-senior students to be success. It does not matter which one you define as success or failure, as long as you only got two outcomes. They just need to identify two different outcomes. Doesn't matter which one is what. So similarly, right, I can ask, do you live on campus or off campus? That's the only two possible answers you can give. Each one of you will be in one out of the two categories. So again, I can define living on campus is success, off campus is failure, or on campus is failure, off campus is success. Or if I ask, do you have a job? Right? I can define having a job as success, not having a job as failure. Or I could define having a job as failure, not having a job as success. So it doesn't matter as long as you only got two outcomes. Then we need to use this binomial probability distribution that uses a different set of formula. So the formula in binomial probability function is, so look at f of x, right? This is zero probability. So probability now equals n factorial, where n is the number of observations, divided by x factorial times n minus x factorial. So it's the number of success factorial multiplied by the number of failure factorial. Then multiply by probability of success raised to the power of success, raised to the power of the number of success. Then finally multiply by the probability of failure raising to the power of the number of failure. So it's a seemingly long formula, but actually it's not that bad. You only need three numbers. You only need x, n, and p. Again, n is the total number of observation. X is the number of success, and the p is the probability of success. Right? If I have again, 18 students in this class, my n would equal to 18. If I want to figure out what's the probability, right, among 18 students that 10 of them live on campus and the other 8 lives off campus, then my x would equal to 10. And through historic data, if we know that, 40% of the students live on campus, then I will plug in p equals 40 and then do this calculation. So it does require you to understand what is x, what is n, and what is p. But once you have those 3 numbers, you can plug in and calculate. If you haven't done this for too long, you might forget what factorial is, but I'm showing you here. The calculation of n factorial equals n times n minus 1 times n minus 2 times n minus 3 all the way until 1. You just keep multiplying, like reducing one number at a time and until you reduce to 1. That's n factorial. But other than that, it's a straightforward process. Although, yeah, you do have more components in this formula. But remember, this formula only applies to binary outcome. So the chance that you use this is relatively low. Again, only for those yes-no situations. If you got more than 2 different outcomes, right, what department are you coming from? You certainly got more than 2 outcomes. Then you don't use this formula. You go back to what we learned earlier. So not so high of a chance you use it, but you do need to learn. And again, later in the semester, you will see a lot of problems talking about proportion. So all the proportions are talking about the success in a binary event, right? The proportion of students living on campus. Okay, maybe 40% of the students live on campus, maybe 50% of the students live on campus, right? Proportion is later what you will also see to describe the binary outcome. But we just focus on chapter 5 here, and we can do one practice for this new formula. So here, let's see how can we translate a real-world situation into statistics. A company is concerned about retention. In recent years, management has seen a turnover of 10% of hourly employees. Therefore, for any hourly employee chosen at random, we estimate a probability of 0.1, right? That the person will leave the company next year. So usually, if you see something like a clearly stated, usually, again, I'm not saying you have to, but usually or the easiest is to define this as your success. Because the probability is already given, you can simply plug in the probability of success. So use what's already pointed out, what's defined to be your success. And then the other outcome will naturally become failure. And then, right, if you use 100% minus the probability of success, you naturally get the probability of failure. So the question now is choosing 3 hourly employees at random. Right now you have a total observation of 3. What is the probability that one of them will leave? So in other words, we're trying to figure out the chance that 1 out of 3 leaves, but the other 2 stays, right? So the other 2 are having the 0.9 probability, but only this one have that 0.1 probability. So, but how do we calculate precisely the f of x, right? The combined probability from 3 people, not like 1 person. And going back here, now I'll give you a minute to think through and then tell me what value is x, what value is p, and what value is n. You can just unmute yourself or you type in the chat window. I wanted to see who gets it. So think about it. Binary outcome. The employee is either going to leave the company or to stay with the company, like binary outcome. Leaving the company has a chance of 10%, meaning staying with the company has a chance of 90%. Now we're looking at the 3 employees only. What is the probability that 1 out of the 3 will leave, but the other 2 stay? Anyone? So first of all, what do we want to define as success? What's the easiest? Okay, let me see. 10. So n equals 3. Yes, we only got 3 people to look at. So when you say p equals 0.9, right, you are saying probability of success is 0.9. So now my question is, what do you define as success? Do you define? Okay, so okay, yes. So if leaving the company you define as a failure, then yes, staying will be your success. And then here we got 1 person leaving and 2 staying. So we're saying we got 1 failure, but 2 success. So if your p is 0.9, then your x would be 2. Right, we define the success as staying. So we say 1 of them leaves, but then the other 2 stays. Yes, yep. Yes, so that is one way to define. And in that case, how do we plug in? We would have 3 factorial divided by 2 factorial multiplied by 3 minus 2, which would be 1 factorial, right? So your denominator will be 2 factorial times 1 factorial. And then p raised to x, that would be 0.9 raised to the 2nd power. 1 minus p raised to n minus x would be 0.1 raised to the 1st power, right? This whole calculation. So yes, that's one way to do it. Was there anyone who used who defined success as leaving the company. So n would still equal to 3. Then how does your p or x will change? Yes, very nice. Ken got it. So if you flip it around, right? If now you define leaving as success, then P would equal to 0.1. And then now you have one person leaving, 2 staying, then your X would equal to 1. And then the interesting part, if we do the same plug-in, you would still have 3 factorial in the numerator. And you would still have 1 factorial times 2 factorial, right? Versus 2 factorial times 1 factorial. So you have the same number in the denominator. And now you have 0.1 raised to the first power, and then 0.9 raised to the second power, which again was the same. When we defined staying as success, right? We had 0.9 raised to second power, then 0.1 raised to the first power. But now we simply flipped the 2. So that's why I'm saying earlier that it doesn't matter which one you define as success, which one you define as failure, because you are multiplying everything together. And that gets you the same numerical outcome. That's 0.243. So now my question is, how do you interpret this 0.243 when we go back to the exact question? What is that probability? What's your understanding of this number? Who can try to interpret what does this number mean? Right, looking back to the question, right, what I was asking, and you did all the calculation. Now you are saying, okay, f of x or f of 1 or f of 2, right, f of x equals 0.243. And people are like, what does that mean? Yes, yeah. 24.3% probability that 1 out of the 3 employees will leave, or more precisely, if we only have 3 employees, 1 of them will leave, but the other 2 will stay. So that's precisely what we're talking about. We're analyzing a very specific situation. We only look at the 3 employees. Among the 3, 1 would leave, but the other 2 stays. But that's not the number you can use in any scenario. It's not 1 out of 3, right? Like for example, I have a team of 8. I can't use that number. I can't use 0.243 because actually my n equals 8. And then I will need to redo the calculation and I'm going to get a different number. So if you have a team of 3, that's the number you get to use. But your team size is different, or your expectation of people leaving is different, then your n will change and your x will change. So depending on the exact question you are answering, the probability will be different. It is not the same across the board. So that's the interesting part of statistics. You can solve a very particular question, while later you can also generalize something. So that's the calculation. And just to help you understand, I'm also showing you a little more details. If you get to think it through step by step, right, you can think it in the way that the 3 employees make their decision independently. So each of them only have to choose between to leave or to stay. And their decisions are not depending on others' decision. Right, so worker 1 will simply choose, do I leave or do I stay? And regardless, right, if worker 1 chooses to leave, worker 2 gets to choose, do I leave, do I stay? Or if worker 1 chooses to stay, worker 2 still have to make the same decision. Do I leave, do I stay? Right, so those are independent. And then worker 3 gets to make his decision. And with the combination of the 3 steps, well, which actually happens simultaneously, it doesn't have to be sequentially. What we are looking for is out of the 3, right, 1 decides to leave, but the other 2 decides to stay. So there are 3 scenarios that satisfy this expectation. Scenario 1 is worker 1 chooses to leave, but worker 2 and worker 3 chooses to stay. So if we bring in the probability 1 by 1, the multiplication gets us to 0.081. There is a second scenario that worker 1 and worker 3 decides to stay, but worker 2 decides to leave. So that 3 probability gets us to 0.081 as well. And a third scenario that worker 1 and 2 decides to stay, but worker 3 decides to leave. Then putting together those 3 probabilities, we got 0.081 as well. And adding up the 3 probabilities, we got a total of 0.243. That's what I'm showing here. So again, that's the probability of choosing 3 employees at random. 1 of them will leave, but the other 2 will stay. That's the exact probability. So any questions so far? We're good? No question, no question. Good. Okay, very nice. So that's a probability calculation. And then, like I said, it's a special situation or special case. So we use a slightly different formula. Now, when we calculate the mean will simply equal to n times p. It's just your sample size times the probability of success. The variance will be n times p times 1 minus p. So it's sample size times the probability of success and times the probability of failure. And the standard deviation, same as always, positive square root of the variance. So that's the simple calculation for probability distribution. If we apply the same formula, right, in this case, we will calculate the mean, right, or you can call it the expected value is 0.3. The variance is 0.27, and the standard deviation is 0.52. So you can do those exercises on your own, and I have all the correct numbers listed. Just to show you, this applies a different set of formula. And this different set of formula is only used for binary outcome, only when you got success versus failure. In all other cases, when you can have more than 2 outcomes, you use the regular like x minus mu, that formula. So that's all for chapter 5. The foundation of probability distribution. When we dive into chapter 6, now we are normalizing and standardizing continuous and discrete random variable together. We're creating a standard method that can analyze any type of probability distribution, and like I said, can identify where your x value is given the entire curve, right? Are you on the right-hand extreme, or are you in the middle? Are you on the left-hand side? Where you are given everyone else. So we will learn that in chapter 6, but let's take a 10-minute break. We're 12:25 now. Let's all come back at 12:35. Get some water, stretch, relax a little bit, and then I'll see you in 10 minutes. Then we can start. So let's dive into chapter 6. Still talking about probability distribution, but now we normalize everything to be continuous. The key concept is that it is not really possible or practical to talk about a probability of a random variable if it is continuous. Because we have seen the, let me go back. So we have seen the, where was my distribution? We have seen the histogram of a discrete random variable distribution, right? And in those cases, x takes discrete value. So there's a clear like 0 or 1 or 2 or 3, and there's a gap between each value. So you can see clearly which bar it is, right? And how tall the first bar is, how tall the second bar is. So it works well when you have a discrete random variable. You may have 5 bars, you may have like, where is it? You may have like 3 bars in the other example, but what I wanted to show here is that as the number of outcomes start to increase, right, your x value can take on, let's say, 20 different values. Then you are going to have 20 bars. And then again, look at here, your bar chart will start to get very crowded. And imagine if you have hundreds or thousands of x values, and that's what you are going to have in continuous random variable. Because continuous random variable, there's no limits, there's no gap. You can literally take any value, take millions of values. So in that case, it's not manageable, right? You can't literally draw millions of bars if you want to see, okay, what's your income level? And you survey every single person, and then you draw the bar for every person. Maybe someone makes 50,000 a year, but someone's like 50,250, and someone else is 50,310, right? You're going to have so many different values. So then it becomes not manageable. So you don't want to have millions of bars and all crowded right next to each other, and you're not able to see which bar is which. So in that case, when you have a continuous random variable and x can take unlimited values, and you are going to have unlimited number of bars to show the probability distribution, you will ultimately just have a curve. So instead of having millions of bars, we make it a smooth curve to cover the entire range, right? To cover the range of 0 to 200,000, to cover the entire range. And then instead of looking at a tiny bar, now the new technique we want to learn is, now we're looking at the area beneath the curve. So the area beneath the curve in this probability distribution, in this bell-shaped curve, represents probability. So now we are transforming a probability or algebraic problem into a geometry form, right? So geometrically, when we want to visualize the probability, now instead of the height of the bar, now it becomes the area in the curve. So for example, the probability that x takes on a value between some lower value x1 and some higher value x2 can be found by computing the area in the graph over the interval between x1 and x2. So look at the darker gray. If we can calculate the area of that section, that becomes the probability of x taking those values. So someone talked about temperature earlier, right? We're looking at, okay, is it 68 degree now? Is it, I'm 68, and then there are cities that's 70 or 71. There are also places that's 65, 66. So with that in mind, and we know temperature is continuous, right? Maybe 68.5 or 67.752, or maybe 70.315. So given that, if we want to say randomly, when looking at all the cities in California, what's the probability that the temperature fall between 68 and 70 during this hour, right? This noon hour. What's the probability? So we're covering any value between 68 and 70. Maybe 68.01, maybe 68.0005, maybe 69.23516, right? All the values in this range is covered. So that probability can be figured out by calculating the area of this darker gray between x1 and x2. So does that make sense? Now how we transform the probability from the height of the bar into the area in the curve. Yes, no? Yes, Brenda got it. What about everyone else? Karina got it. Good. Hector, nice. Okay, good. Yeah, because it is a little tricky, right? We have been looking at the histogram, we have been looking at the height of the bar, but now we make it an area. So it looks more like a geometry question now, which is fine. we are going to have new formula to calculate the area. So we will get there in a minute. So now since we are transforming it to be a geometric problem, now we want to go back to the shape, right, to look at the distribution. Remember, we learned it last week. In a perfect world, we want the normal distribution to be symmetric. And we want the mean, the median, and the mode all to be at the center, the exact middle, right, with the highest probability in the curve. So that's where you see the center. That line is. It is the mean, the median, and the mode. So it is the average. And by definition, when it's a median, right, then it means 50% of the data points are smaller than this value, and 50% of the data points are larger than this value. So that's why you have area equals 0.5 and 0.5, right? That's 50%, 50%. And also by definition, if it is also the mode, then it means this value has the highest frequency or relative frequency. Then the frequency will go lower, right? Probability goes lower as we deviate away from the mean. When you go to the extreme, right, the right-hand side and the left side end, the probability is approaching to 0. That means very low probability. Now look at the homework score. The center is probably 88. And then, yeah, maybe I got one student having a perfect score. And on the left-hand side, I got a 0. There's one student didn't turn in homework too. Those are rare cases. But there are some students getting like 92, 96, some other students getting 84, 80, or even 76. So those are like slightly lower probability, but the majorities are 88 or 92, but so that are in the center. But then the further you are away from the center, the lower the probability. So that still matches what we learned before. Now we just wanted to emphasize two metrics. One is again the center, and the other is the variability. So remember, we always want to use the mean in the probability distribution to describe where the center is. So it simply tells us, do we have a group of large number or do we have a group of small number? So that's simply what we look at. Is it on the left end of the curve? Is it on the right end of the curve? Like where the center is. We also learned about the variability. And in the context of probability distribution, we usually use standard deviation to measure the variability. So we learned that the larger the standard deviation, the more variability we have in the data set. But the smaller the standard deviation, the less the variability. And when you translate that into a shape, right, in geometry, you will see when standard deviation is large, your curve tends to be wide and flat. Simply meaning you have a lot of different values. The value could go very large, could go very small. It can be anywhere along the interval. So large variability, that's all you're saying. That's when standard deviation is large. Sometimes you have small standard deviation. So look at the tall and narrow curve. You see the right end and the left end. They don't go very far, right? They are still pretty close to the center. It means You don't have too large values and you don't have too small of a value. All the data points are pretty close to the mean. You don't have too much variability. All the data value looks similar, no extreme values. So then high frequency, right, in this middle range. It's like, okay, if the mean is 88 and all the students are somewhere between 92 and 84, that's not much variability. Everyone's at the same page, no differences. Everyone makes 1 or 2 mistakes and that's it, right? Not much differences versus if one gets 100, but the other gets 48, right? That's huge difference. So that's what standard deviation is measuring. And we can visually see that, right? We can observe that clearly just by looking at it. So that's something we need to be able to tell by observing a probability distribution. So that's the basic concept. Any distribution, any probability distribution can be described just using these 2 terms, the mean and the standard deviation, right? If you look at the green, the light blue, the dark blue, the purple, you only need the mean and the standard deviation to describe, and you can see how different they are. So that's one thing. The other is, I wanted to give you some general idea on how to do some high level estimation. So assuming you don't have calculator with you, you don't have pen, you don't have pencil, you don't have anything, but people were telling you, oh, this number is about 1 standard deviation. That's about 2 standard deviations, right? If people start to telling you this, but you don't have anything in hand to calculate anything precisely, how can you make some vague estimation that's in the ballpark? Again, not necessarily too precise, but gets you in the right direction. So we then want to use what we call empirical rule. You will get this in the homework. In homework, I do ask you to use empirical rule to estimate a few things. So what is empirical rule? Empirical rule simply tells us when we look at the symmetrical curve and when we start from the center, right, start from the mean, if we go above and below 1 standard deviation, right, mu plus 1 standard deviation or mu minus 1 standard deviation. So going above and below 1 standard deviation, we are actually covering 68% of the data points. So that's the majority of the data. It's more than 50%. It's close to 70%, right? 68% of the data points are actually just within 1 standard deviation. So what that tells you is, for example, right, if I tell you in homework 2, the mean is 88, the standard deviation is 4. And if you are a 92, right, you are exactly 1 standard deviation above the mean. So when you have the question like, well, I'm certainly higher than the mean, but am I the top students, right? Like, am I the top 5% or am I top 10%? Am I top 20% or am I really just like 50, 51%, right? If you want to estimate where you are compared to everyone else without knowing everyone else's score, right? That's confidential information. I can only tell you aggregated, where is the mean, what's the standard deviation. With that, you can actually do your calculation. You know that starting from the mean, within 1 standard deviation, there's like the majority of 68%. So if you are in this range, you are basically just right the average, right? The average student. So you are within that range. I mean, it's still good, but it just means it's nothing special. It's the majority. That's what it tells you. Anything within one standard deviation, above or below, right? If you are getting 84 and you are worried, oh, I'm lower than the mean, but how bad it is. Like I'm at the bottom of my class. No, if you are within one standard deviation, you are just a typical average student. You are in this range of majority. So that's what it's telling you. So within one standard deviation, we got 68% of our data points. If we keep going, right, we go from the mean one standard deviation, if we keep going 2 standard deviations, mu plus 2 sigma or mu minus 2 sigma, we actually cover 95% of the data points. So this is more of a threshold. If anything is within 95%, it's sort of the most of the data point. That the 2 standard deviations separates the normal versus the extreme, the special ones. If you are still within 2 standard deviation, right, you are within 95% of the data points. But if you go even beyond that, if you go 3 standard deviations above and below, this range covers 99.7%. So it's almost 100%, but again, we usually have some extreme values. The extreme value, right, doesn't get us to 100%, but it really means almost everyone else should be within this range, right? So when I talk to other people, again, I would say the mean is 88, the standard deviation is 4. So anyone with statistical knowledge should be able to figure out that probably, right, the highest is like a 96 in my class, and the lowest is like a lowest should be something like 76. So that's the range we go, right? Because that covers almost 100%. Or even if you just go 2 standard deviations, sorry, 2 standard deviations is 96 and then 80. That's 95% of my students. So the majority will be somewhere between 76 and 96. But then in the range of 76 and 100, right? If you go 3 standard deviations, that should cover everyone. And also, if you are the one that's 3 standard deviations away from the mean, you can be almost certain that you are a special case. Your score or whatever you got is very different from the majority. It's not within the same range, right? You are a special case, not the same as the majority. So that helps you do some high level estimation. And you will see people say this. People will say, oh, this case is 3 standard deviations. And that simply means it's a rare case. Anything beyond the 2 standard deviation is a rare case. Very uncommon. Your majority of the observations don't have that. So that's what this empirical rule tells you. You don't need a calculator, right? You just memorize 3 numbers, 68%, 95%, 99.7%. That's all you need to know. It's quick and simple, convenient, but the limitation is also obvious. You can only go whole number of standard deviation, and that's not practical. your whole number of standard deviation gets you from 88 to 92, but what if you get 90? What that standard deviation is that 0.5 standard deviation, right? Where does that get you to? What about you getting a 93? What percentile are you then? So then we will need a standardized procedure to calculate precisely what percentile you are. And then that will need to utilize a standard normal probability distribution. And this standard z-score. So this is the single most important thing in today's lecture. And we are going to use it throughout the whole semester. So I want you to pay a lot of attention to be super clear on this, what a z-score is. So the standardized z-score is how far above or below your individual value is compared to the population mean in unit of standard deviations. So key point is how far above or below. Right? So again, if the mean is 88, if you are a 92, you are above. But if you are 84 or 80, you are below. But how far are you 4 points above or are you 8 points below? Right? I mean, that's simple. Your x minus mu, right? The deviation. But we wanted to standardize that. We're talking about the score. We're talking about the temperature, count number, how many people, right? Volume and the distance. Those are all measured in different units. How can we standardize all those different units? So we don't measure it by points or miles or pounds or minutes. We don't use those units. The unit we use is, see here, in unit of standard deviations. So we standardize the difference between x and mu by divided by standard deviation. Right? This in your data set, this is how much variability you have. By that standard, are you far or are you very close to the mean? So we standardize it by standard deviation. So it's a simple calculation. Z-score equals x minus mu divided by sigma. So it measures how far above or below, right? If you are above, it should be a positive number. If you are below, it should be a negative number. And how far above or below in unit of standard deviation. So obviously divided by standard deviation. So that's a calculation of z-score. I want you to check, does it make sense what this thing is measuring? Do you all understand what is z-score? Melissa got it. Karina, good. Brenda, Hector, good. Okay, good. Yeah, so this is a very important concept. Throughout the semester, we keep using z-score and later you learn t-score, but they all measure how far above or below your value is in unit of standard deviation. So it's a standardized value. And once we get this standardized value, we need to convert it to probability. So the way to convert a z-score to a probability is that we will need the standard normal probability distribution table. But don't worry about it. You can easily find, you can Google it, or in the textbook I uploaded, it's like up front. When you open it, you got z-score table, right? The cumulative standard normal probability table. In some other versions, you got it in the appendix, but usually the very first table you get in appendix should be this table. Again, it is the cumulative standard normal probability table. It needs to be the cumulative. If you Google and find a version that's not cumulative, you will get a different set of number, and that doesn't mean the same thing. So make sure it's cumulative. But again, just use the textbook I give you, and everything is standardized. So when you look at your standard normal probability distribution table, you only got the 2 dimensions, right? The row and the column. You don't get anything else. Usually, the row will range from negative 2.0 to positive 2.0 with 0.1 increment. So you will see negative 2.0, negative 1.9, negative 1.8, negative 1.7, all the way to 0. And then you will have 0 and then 0.1, 0.2, 0.3, all the way to 2.0. That's what you will see in the row, which represents the first decimal place of your z-score. So your z-score may be positive, may be negative, because if your value is greater than the mean, you got it positive. If your value is lower than the mean, you got a negative value. So z-score can be in both directions, but the row indicates the first decimal place. And usually, your z-score will have 2 decimal places. And the second decimal place is represented by the column. So your column will have 0.00, 0.01, 0.02, 0.03, all the way to 0.09. So that's the second decimal place. So if your z equals 0, right? Z equals 0.00, meaning you are looking at the exact center, right? You are not deviating from the mean by a little bit. If I tell you the mean is 88, and you're like, that's exactly what I got 88, right? So x minus mu, you have 0, right? 0 divided by standard deviation for your z-score equals 0. So if your z is 0.00, you just get to read row 0.0 and column 0.00. Right? That's a z equals 0. And what it says, 0.500. So the number you see in the table is the cumulative probability. In other words, it is the area to the left-hand side in the curve. So again, if you are looking at the center, right, you are not deviating from the mean even by a little, then you know by definition, you got 50% of the values to the left-hand side. So that 50% is this 0.5, or meaning 50%. That's how you read the table. Show you another example. If your z-score equals 1.34, right? Someone got a higher score, higher than the mean, and then you do x minus mu divided by sigma, and you got, okay, z equals 1.34. How do you translate this into a probability, right? Or percentile? Now you go to the table. What's the first decimal place? First decimal place is 1.3. So you get to look up, I'm trying to find, you get to look up row 1.3. So that's the right row you look at. And in the row, you got 10 numbers. What's the second decimal place? Second decimal place is 0.04. So then you need to find the right column. Many numbers in the same column. But all you need to do is find the intersection of row 1.3 and column 0.04. And then in the intersection, this is the number you find. 0.9099. So again, that's the cumulative probability. What's a cumulative probability? Look at the chart here. The yellow area is this 0.9099, meaning 0.9099 probability, or over 90% of the time, the data points in this data set is less than what you got. Right? Remember, to the left-hand side is all the small values. The right-hand side are all the large values. So over 90%, right? 0.9099, almost 91% of the data value are less than, like smaller. Only approximately 9%, right? 9 to 10% are higher than you. That's on the right-hand side. But again, what's shown in the table is the yellow area. It's the cumulative probability. It's the area to your left-hand side. It's a probability of all the value less than what you specified. So does that make sense? Yes, no? I know it's getting more complicated. Wanted to see if it's making sense. Yes, Brenda, good. Yeah, so think like, okay, if you got 91 and you calculate, okay, I got a z-score of 1.34. Where am I compared to other students? Am I still just the middle portion, right? 91 isn't too, or like 93 isn't too far from 88. It's like, am I still just an average student, or am I already somewhere outstanding, like good? Well, if your z is 1.34 and this is what you get, that means, like I said, approximately 91% of other students are lower than or equal to your score. Only approximately 9% of the students are higher than you. So you are approximately 91 percentile of this class. So that's all it's saying. So without looking at other people's individual score, right? Just by looking at the aggregate, the mean, the standard deviation, you are able to calculate where you are compared to everyone else. So that's what z-score and this standard normal table is used for. It's for us to locate any value along the interval, to see how many values are greater than it, how many values are smaller than it. That's what we're doing. So with that, let's solve just one real world problem. Once we solve this, we're good today. So this is a perfect example on how to use standard normal probability distribution to solve a business problem and improve business performance. It starts with identifying the problem, then to the fix of the problem. You will see how do we go step by step and finally make a different decision or provide a recommendation. And this is important in terms of translating a business problem into statistical language, do all the statistical calculation and operation, and bring it back to business. because ultimately you need to be able to make a recommendation that's actionable and people can do it. So it involves this two-way translation. You get to understand the business problem, translate it to statistics, do all the statistics and translate it back. So we'll do it together. So here in this example, a shop sells auto parts and supplies, including a specific motor oil. So currently their strategy is when the stock of this oil drops to 20 gallons, they will reorder it. And after they place the order, they have to wait until the oil to be shipped to the store. Usually say it takes 3 days to get here. But during the 3 days, right, they only have a stock of 20 gallons. So in this situation, the store manager is concerned that sales are being lost due to stock out while waiting for the order to arrive to his shop. So again, what's the exact situation when we're waiting, right? In the 3-day window, when it's being shipped to the shop, we only have 20 gallons. If a customer comes in and say, I want 5 gallons, no problem, right? We can sell it. Or if a customer comes in and say, I want 15 gallons, that's also okay, right? We can sell. If a customer comes in and say, I want 20 gallons, we'll be like, okay, that's all I have. Here you go. I mean, those are the okay situation. But what the manager is concerned is that if a customer walks in and say, I want 21 gallons, then you will have to say, well, I'm sorry, I only have 20. I don't have that much. And then maybe the customer will just turn around, no, then I'll just go somewhere else, right? Or if someone comes in and say, I want to buy 25 gallons, but then no, I only have 20, and then he's not happy. No, I'll go somewhere else, right? So if the demand during this 3-day waiting period is greater than 20, you have a problem, right? You're losing sales, you're losing customers. So the manager is concerned about this situation. And in order to really manage the business, the manager needs to know what is the probability that this situation happens. If there's a low chance, right? If only 1% of the time you can't meet the customer's need, that's okay. But if half of the time you can't meet their need, then there's a huge problem. So the manager would like to know the probability of a stock out, right, during this waiting time. In other words, what is the probability that demand exceed 20 gallons during this 3-day period? And historic data shows during this waiting period, the demand has the distribution of demand. Some customer needs less, some customer needs more, right? So the distribution of demand had a mean of 15 gallons and a standard deviation of 6 gallons. So with that, how can we calculate the probability of demand greater than 20? So does this make sense? What business problem we are facing? Yes, no? Makes sense, good. Melissa's good. Karina, makes sense. Okay, good. So now we understand the business problem. And now let's try to link it to what we just saw earlier, So we've seen this, right? So if we know that demand, right, the distribution of demand has a mean of 15, then we know that the center here is 15. Oops. So we know the center is 15. And we know, okay, it varies. Some customer wants more, some customer wants less, right? We know there are large value, small value, and we just know the standard deviation equals 6. But the other key value we need to know is, for now, what we have, right? So now we have the reserve of 20. Oops. I mean, yes, we know 20 is greater than the mean. But again, is 20 enough? Because there are people who needs more, right? It's still reasonable if someone orders 21 gallon or 22 or 25, right? There's a large range. So we know here we got 20. And practically, right, we know that if the demand is less than 20, 1 gallon, 2 gallon, 5 gallon, 10, 15, 16, all the way until 20 gallon, there's no problem. So the yellow area, right, in this curve means no problem. We can serve the customer. What the manager worried is the red area. See where I'm highlighting, right? That's the area where demand exceeds your stock, right? If maybe it's 21, maybe it's 22, maybe it's 25, maybe it's 28, right? That's the situation that gets us into a problem. So the question now is, the manager wants to know, what is the probability of this problem from happening, right? Is that a 1% probability, or is that a 50% probability, right? What's the chance that I'm losing business, I'm losing customer? So does it make sense when we translate it into statistics? Like the left-hand area, the right-hand area, right? When the situation where we're okay, but the situation when we're not okay. We all understand that. Like when I draw it on the curve. Yes? Good, good. Everyone else? Brenda, Melissa, good. Hector, good. And Jason, you guys good? Mikhail is quiet today. You good? Sharina, good. And good. Okay. Okay, so okay, Mikhail, good, nice. Okay, so that's the situation we're facing, right? And now by translating it into this curve, now we know which area we need to figure out. And we know that is the exact probability, right? It is the probability of 100% minus the yellow area. So then the question translates to, then what is the corresponding z at this point? Because if we need the probability, right, we need the z-score to look up in the table. So by doing this backward induction, if we want a probability, we need to calculate the z-score so we can do the mapping from the table. So now the real question becomes, how do we get to the z-score? So who can answer that? We saw the formula, right? Z equals, who remembers what's Z? What's the formula again? Z equals, remember it measures how far above or below, right? X minus mu in unit of standard deviations. So X minus mu divided by sigma. We should be able to get our Z scores through this formula. And now the ultimate question is, what are the numbers we get to plug in? What's X, what's mu, and what's sigma? We only need the 3 numbers to calculate. So who can answer that? Anyone? So think about X. Well, sorry, think about sigma, right? Sigma is the standard deviation. And what was our standard deviation? Look at here. The normal distribution with a mean of 15 and a standard deviation of 6. So what's our sigma? Yes, perfect. Sigma is 6. Yeah. Oops, let's go back. So sigma equals 6. Now let me write. So it's getting messy. Sigma equals 6. So denominator, we got 6. So Melissa did a great job. Who else wants to continue to tell us what's X and what's mu? Anyone else? Oops. What's mu? Mu is population mean, right? We've said historic data said population mean is the mean demand is 15 gallons. And what's X? X is what we have, right? That's exactly our situation. So we have a stock of 20 gallons. So that should be the number we plug in. Like we have a stock of 20 gallons. We know the average demand is 15 gallons with a standard deviation of 6. Now we wanted to see what is the probability of X greater than 20. Right here, with a mean of 15 and the standard deviation of 6, what's the probability of X greater than 20? So we use the formula Z equals X minus mu divided by sigma. So 20 minus 15 divided by sigma, Z equals 0.83. So that's the Z score. Now, if I'm looking at the Z table, who can tell me what's the corresponding probability of Z equals 0.83? Which row, which column should we be looking at? Anyone? Very nice, Melissa, great. See, we are looking at row 0.8 because that's the first decimal place. And the column of 0.03, very nice, Karina, you also got it. See, the intersection of row 0.8 and the column 0.03. It's just a lookup. we look up the probability, right? The yellow area equals 0.7967. So there is a 0.7967 probability that demand will be lower than or equal to 20 gallons. That's what we directly look up. But that's not the answer to the question. Because the question is asking, what is the probability that the demand exceed 20 gallons? So what's the last step we get to do? Once we figure out the yellow, what's the last step we need to do?
Subtract from 1.
Yes, perfect. We just need to subtract, right? Use 100%, subtract the yellow area, so we get the right-hand area, which is 0.2033. So that is a probability. So the probability of demand exceeding 20 gallons, right? All the large value on the right-hand side, that probability is 0.2033. So in other words, now we have the manager calculate that there is an approximately 20% chance that we have a stock out problem. 20% chance that demand will exceed 20 gallons when you only have 20 gallons in stock. So that's the probability of losing sales, which isn't a good situation because 20% is 1 out of 5. We don't want to lose business every 1 out of 5, right? That's a high probability. So we wanted to fix this situation. So as the manager realized, see, this is exactly what we were showing, right? Area 0.7967 on the left-hand side, then one subtract that, 0.2033. So when the manager realized this situation, he wanted now to reduce the stock out risk from 20% to lower, to only 5%. And now the question becomes, then what should be the reorder point? We know that if he only reorders when the stock is 20, there isn't enough. So he shouldn't wait until 20. He should have more stock to prevent the problem. But the real question is, okay, we know that's 20, but should the reorder point be 21 gallons? Or should he reorder when he has 25 gallons? Or should he reorder at 30? Right? So that's a real business question. Again, where the reorder point should be. We know 20 is not good. But what number is a good number? Right? We don't just randomly come up with it. We don't just say, oh, 25 or 30. Like, no, it comes from careful calculation in statistics. And here we got a hint. Right, so what we are trying to do is to reduce the darker gray, reduce the size of this area from 0.2033 all the way to 0.0500. So we wanted to reduce from 0.2 to 0.05. So we basically pushed the threshold to even further to the right-hand side. So it means, right, at this point, this threshold should certainly have a larger value, right, of x, where your reorder point to be, because you push it all the way to the right-hand side. But how do we calculate x value? All we can know is X value is part of the z-score calculation. We know z equals x minus mu divided by sigma. And Melissa just told us earlier that sigma was 6 and mu was 15. So 2 of the components we already know. Now, if we need to figure out x, right? Because again, that's exactly what we're looking for. We need to figure out the reorder point. If we need to know x, then we actually need to know what z is. If we know z, then we can solve a simple equation, right? Reverse engineer, move sigma to the left-hand side, move mu, and then we will know what x would be. So now the question changed to what is z in this situation? If you have a 0.05 on the right-hand side, and you naturally have 0.95 on the left-hand side, right? That's this light gray area. Light gray area is 0.95. Can you tell me what the z-score is? Anyone? Let's see what we're trying to do, right? So we're trying to find the z-score that has an area of 0.05 on the right, but 0.95 on the left. Then the question is really from this table, can you find a z-score that has a probability of 0.9500 or very close to 0.9500? Can you look up the value from the table? Because if you are able to find that 0.9500, you can simply find which row it is and which column it is. Then you know the. Very nice. Okay, Christopher, you got it. Yep. So Christopher found, okay, we got 2 values very close to 0.95. We have a 0.9495 and a 0.9505, right? Those are the closest value to 0.9500. Actually, the exact middle point here would be that 0.9500. So what corresponding z-score is, just need to see which row. Row 1.6, then which column? It's either column 0.04 or 0.05, or you can even say 0.045. I mean, all of those are within the buffer zone. If you write 0.04, you get it right. If you got 0.05, you also got it right. Like I said, I built in a buffer zone for all the fill in the blank. So that's the correct range. And if you do like exactly in the middle, 0.045, that's even better. So do we all understand how to get the z-score by looking up 0.9500? Yes, Melissa, good. Karina, Brenda, good. So this, okay, Christian, good, very nice. This is the exact reverse process, right? In step 1, we got a z-score and we look up probability. In this stage, now we know a probability, but now we look at z-score. So you see there's a one-to-one mapping. It can go both ways. So now the good news is, okay, we figure out z. And then I just showed you, right, z equals x minus mu divided by sigma. So we can simply plug in, right here, we found it. And we can simply plug in, and then by moving things around, just solve a simple equation. and I can write it for you. The simple equation we're solving is, right, z equals 1.645, z equals x minus mu, meaning x minus 15, divided by sigma, which is 6. Right, so in this equation, only x is unknown. So we can just solve the equation by doing this. Right, I'm listing all the steps on how to do the calculation. So once we do that, we can easily get that x equals like 24.87. If I ask you to round up to a whole number, you can round up to 25. So the implication here, right? I mean, we did all the calculation, all the lookup. That's very technical, very intense. Now the question is, what is this number? What does this mean? Right? It is the exact reorder point. It means a reorder point of 25 gallon will change the probability of a stock out to be only 0.05. Right, that's this area. So only 5%. And now looking at this whole process we just went through, right? We look at our historic demand, where's the mean, where's the standard deviation. We look at our current strategy, right? When to reorder. Currently, we reorder at 20 gallon. And we calculated the probability of having a stock out problem, which is a probability of 20%. And we wanted to reduce that probability from 20% to 5%. And we reverse engineer, calculated that in order to have that 5%, the reorder point should be 25 gallon. So this is the practice that by raising the reorder point from 20 gallon to 25 gallon, now we reduce the probability of a stock out. We reduce that from 20% chance to only 5% chance. So it is a very significant decrease in the stock out risk. And now the shop has a much higher chance to meet the customer's desire, right? There's a much lower risk to lose sales during this waiting time, because now we have enough stock, or there's a much higher chance we can serve our customer. So that's using statistics to solve a business problem and improve business operation. It does require two-way translation, right? What's the situation we're facing? What's the statistical operation, right? Do the calculation, look up in the table, then go back. It is comprehensive. It's not easy. I agree. It's a little tricky. But once you get familiar with it, I mean, this is the first time we use this sophisticated process or this method to solve a real world problem. And we will continue to do that for the rest of the semester. Like I said, the first time this week and the next week, you might find the homework challenging. And it takes you time to really interpret and understand what that number is. Where do I plug that number in the formula? It will take time. But gradually, week after week, we continue to do this exercise, you will feel more and more comfortable. You will be able to do it quicker and quicker. So it comes naturally as you continue to do homework on a weekly basis. And that's the importance of homework. So I've showed you one example, and I told you there's a homework 3, right? Multiple choice, fill in the blank. But in order for you to prepare yourself for the homework, to get a good score in the homework, what I also prepared you is 3 exercise questions on slide 60, 61, and 62. And you can find slide on Canvas. So those 3 pages, I give you a simple question, not even a business problem. It's just simple, where is Z, what's the probability? I give you the question, I give you the chart. I want you to do the calculation on your own to be able to calculate the Z and to be able to find the probability from the table. After you do that yourself, then you can check your answer with what I have on the slide. So all 3 slides, 60, 61, and 62, like all 3 slides have full solution to exactly what are the numbers, what's the final number you need to get to. So that's for yourself to practice. Once you do these 3, you will get a much better understanding and you will feel more comfortable, more confident to solve problems in chapter 5 and 6. So once you do that, you should be ready to do the homework. If you are not able to solve those 3 problems on your own, then it means there's knowledge gap. And you need to go back to the lecture note and go back to the textbook to fill in the gap and then do the homework. It's not manufacturing more work for you. I understand you are busy, you have other classes, you have a job, you have family, we all have that. But it really does good for you. Only when you understand, then you can do well with homework. So you get a good score, because average homework score is 30%. So it's very important that you get a good score in the homework. And I'm preparing you for getting that. So just follow the instruction, do the exercise, make sure you understand, and then do homework. Same as always, you got a full week. Due by the end of Friday, but again, try to do it sooner than later. Don't leave it to the last minute. If you have any questions, email me. Do make sure you use the appropriate email subject, because I do prioritize emails when I got it in the right subject. I try to respond within 2 days. And also I hold office hour. If you have questions, you can email me, tell me which day you want to visit, and I'll tell you which day, what time is the best time for you to get up. So just do all the work you need to do, and also read the chapter for next week. It's very close to, the knowledge is very similar to what we just learned today. Goes a little bit further. Again, it would be beneficial if you come in prepared, but even if not, you are still fine. But I want you to do the best. That's all I'm saying. So that's all for this week. Any last minute question? Are we good? If we don't have last minute questions, then I just, okay, good. Hector, good. Melissa, good. Christina, nice. Thank you. Okay, yeah, have a nice weekend. And I will see you next week. Bye, everyone.